I want to talk a little bit about application of inversion data both to a spectral problem and to a spatial problem, in fact, sometimes both together. So to put this a little bit of background, because Steve warned me that, again, the audience varies a lot in terms of background. I want to talk about an overview of solar flares. Sarah mentioned them this morning a little bit, the day the Earth became electrified. What are they? And a little bit about what challenges they represent. I may have time to dwell on that a little bit, I may not, but just putting it simply, solar flares are big. And therefore, things that would happen in a very short time scale, like if I turn the light switch off, the light goes out. Michael Faraday would argue it doesn't go out immediately. There's an inductance in the circuit that causes the light to go out after about a nanosecond. If you turn the switch off in the sun, simply because the sun is so much bigger and there's such a much higher inductance, it should take about 10 to the 7 years for flares to appear and disappear, and they do so in much shorter time scales than that. So there really is a sort of fundamental challenge to explaining how these things work. So I'll talk in particular about hard X-rays, which are diagnostics of accelerated electrons and the direct observations we use. A little bit about spectral inversion, a little bit about spatial inversion, and try and reach some conclusions at the end. Okay, so there's the pretty pictures. This is the Earth to scale. This is not some hyped up image. This is real. It's IDL color table 3, I guess. But these are erupting prominences, coronal mass ejections, whatever. Lots of pretty pictures of them. This is a thing called the Bastille Day flare. The sun apparently makes more flares on July 14 than any other day of the year. Not sure why. And we have to understand how these things work. Magnetic loops are a clue to this. We believe that these are simply like what the pattern of iron filings would be if you put a horseshoe magnet down and scatter the iron filings around, kind of like that. So all of this phenomena that we're going to talk about, solar flares, coronal mass ejections, and so on, are ultimately have their roots in electromagnetic fields and Maxwell equations, leading to this famous quote that we never really have figured out who said this. We can't attribute it to any one person, but everybody knows it in solar physics, that if the sun did not have a magnetic field, it would be as dull and boring a star as most astronomers seem to think it is. The sun is interesting, A, because it's 8 light minutes away as opposed to 4 or more light years away, so you can examine processes in more detail. But B, it has this magnetic field, which causes all these manifestations of solar activity. The magnetic field is rooted in the solar convection zone, and the turbulence in the convection zone makes the magnetic fields wiggle around, and that gets transported into the thin outer layers of the sun, the corona, where the changing magnetic fields can give rise via Maxwell equations to electric fields, which accelerate particles. Typical energetics, astronomers are used to throwing around large numbers, but just to put it in perspective, this is an ergs. An erg is about the energy that a bug makes when it hits your windshield doing about 30 miles an hour. So this is about 10 to the 31 of those. It's 10 to the minus 7 of a joule if you're used to SI units. Where you see lots of manifestations, we see little bright points here that correspond to loops in X-rays, even gamma rays. We have coronal mass ejections, kinetic energy of ejecta, and so on. And you can look at the various energetics, but they're all of the order of 10 to the 32 ergs, 10 to the 25 joules or so, with percentages roughly equipartition amongst these various things. This is the bit I'm going to be talking about mostly today, are the non-thermal electrons that are making these little blue contours of emission due to a process called Bremsstrahlung. And we believe in this event there was about 10 to the 24, 10 to the 25 joules worth of these things. Okay. Magnetic reconnection is ultimately the process that turns magnetic energy into other forms. You can think of it very straightforwardly as elastic band snapping. If I have a magnetic field the red one going this way and a blue one very close to it going the other direction. If I bring them sufficiently close to each other, then introduce a little bit of resistance in between, the field lines can join onto each other in new ways, the reconnection. And you can think of this as, again, an elastic band. It snaps and drags everything that's on those magnetic field lines very quickly to the left and to the right. That produces kinetic energy, but also in the middle, you have changing magnetic field, which through Faraday's law gives rise to an electric field. And this is a kind of more physically consistent picture of the same thing, but if you like the middle picture, that's fine too. So we get electric fields naturally from the energy release. The electric fields act on the ambient particles and accelerate both ions and electrons. Okay, that was your graduate course in solar flares. We'll talk a little bit about the connection between the observational diagnostic, the so-called hard X-rays, and the electrons that produce them and are the physical objects that we actually care about. When an electron whizzes by an ion, whether it be a proton or a heavier ion in the solar atmosphere, it's simply Coulomb's law. It gets deflected into a kind of hyperbolic orbit. And if you do the math, to conserve energy and momentum, you have to emit a photon that goes off in this direction. It's called a Bremsstrahlung, German word for breaking radiation. And these are the photons that we see. Lots of these collisions occur. The atmosphere is very thick to electrons. The electrons all get stopped eventually as they go through the outer layers of the solar atmosphere. But the photons that are produced are optically thin. They're optically thin. So they escape. There's very little radiative transfer of the emitted photons. So they represent a very good diagnostic, it's almost if you're standing right next to them, of the electrons that produce them. You don't have to worry a great deal about optically thick radiative transfer. So there's the fundamental relation. That the photon spectrum you observe at the Earth, this is just 1/4 pi times an astronomical unit squared. This is the number of target protons in the sun. That's the average density times the volume. So the more target protons there are, the more Bremsstrahlung you'll get, times the electron spectrum multiplied by a thing that, we're physicists, we call a cross-section. It's got the units of centimeters squared per kilovolt. It measures essentially how many electrons it takes to get one photon in a certain energy bin. To a mathematician, they would say, no, this is a kernel. This is simply an integral equation relating the observed, the data, I of epsilon, to the source function we care about, f of e, and the relationship between the two we would call an integral equation kernel. So I call it a cross-section, mathematicians call it a kernel, fine. We know the form of it. It looks reasonably disgusting. It looks something like that. There will be a quiz at the end. But essentially, you can look at this as, it's a function of like three things: the photon energy, the electron energy, and the angle between the two. The angular dependence looks something like this. Photons tend to be beamed in the forward direction that the electrons are traveling in. For different energies, you get different beaming factors. And just because, on average, the directions of the electrons are all different, in particular, the electrons are spiraling around magnetic field lines, so we can do a lot of direction averaging of the electrons. And so it turns out we don't really need to use this thing very much. We can use a kind of angle average version of it, which is a lot more pleasant to use, and looks basically like this. It looks like 1/epsilon e times some logarithmic factor that guarantees that the cross-section goes to 0 as the electron energy approaches the energy of the photon being observed. That makes the math a little more straightforward. If you discretize this integral equation, you can get a data vector of X-ray points at different photon energies. You've got a flux vector of the electron flux at different electron energies. And relating the two is a matrix A that reflects the cross-section and how it varies with both photon and electron energy. The physics is pretty straightforward. You cannot get a 20 kilovolt photon from a 19 kilovolt electron. You need the electron energy to be at least as large as the photon energy, or the process doesn't work. That's not true for all radiation mechanisms, but it is true for this one. Therefore, this matrix is upper diagonal. There is no contribution whatsoever from down here. Again, you can't get a 20 kilovolt photon from a 19 kilovolt electron. The matrix does, however, extend arbitrarily far to the right. If you're looking at 1 kilovolt photons, you can get them from 2 kilovolt, 3 kilovolt, 4 kilovolt, 5, 6, all the way to infinite energy electrons. So the matrix is upper diagonal, augmented, I call it. It is zeros down the lower left corner, but it's not necessarily a square matrix. It's a rectangular matrix. And in principle, with perfect data, you can infer the electron spectrum up to energies much, much larger than the range of the photons you observe. You know, statistics may limit you to observing the photons up to, let's say, 50 kilovolts, but if your math is good enough, you can determine the electron spectrum up to 100 or even 200 kilovolts using only that data, because the 200 kilovolt electrons talk to the 40 to 50 kilovolt photons. So that's the spectral inversion problem. As most of you probably know, but this is basically, can be written as a matrix equation. If you invert it, you get all kinds of problems because the matrix is a very high condition number. The rows are very linearly dependent on each other. The process at 40 kilovolts is very similar to the process at 39 kilovolts. So there's a lot of linear dependence between the rows, and a straightforward matrix inversion magnifies noise to unacceptable levels. We therefore do a kind of Tikhonov type regularized inversion process where we try to minimize this quantity, ideally should be zero, subject to the requirement that some norm of the electron function we're trying to determine is small. Lambda is a regularization parameter. The bigger it is, the smoother the spectrum is going to be. The smaller it is, the more faithfully it will reproduce the observations, and it's always a trade-off between the two. This is the formal solution to that equation, which I'll show you the results of how you apply that in a minute. Okay, so we need some data, and for a long time the theory was way ahead of the data. We simply did not have high enough spectral resolution X-ray data to do this analysis. We had scintillator data, which had spectral resolution of the order of 2. So you'd energy bins like 10 to 20, 20 to 40, 40 to 80, things of that nature. That all changed. There was a couple of balloon flights in the 1990s demonstrating the concept, leading to the launch of this thing called RESI, the Ramadi High Energy Solar Spectroscopic Imager. It was launched in 2002 and lasted all the way through to last October of 2018, when it was finally decommissioned after generating 16 plus years of high quality, like 1 kilovolt type spectral resolution hard X-ray data, giving us literally thousands of events with which to apply this method. Now, I'm looking at the clock and I think I have enough time to do this, so here we go. It's afternoon, we need some entertainment. This is me, a little bit younger, watching this thing launch. It was dropped from an L-1011 airplane because when you're launching a spacecraft, you use most of the fuel getting it up through the first 6 or 7 miles of the Earth's atmosphere, and up to that height, you can get much better payload masses if you drop the rocket from an airplane that's already high enough and traveling at 600 miles an hour in a generally easterly direction. And it looks something like this. I'm going to try this. Did it work? Come on, work. Yes. You drop it. And 5 seconds after it drops, this is the longest 5 seconds of your life if you're watching this, the solid rocket booster at the bottom fires, and off this thing goes, sitting in the payload here, into orbit. Now this is what the scientists want to see. They don't understand all the detailed engineering that goes on behind the scenes, like this.
Hey, what about made you come?
If you've seen the movie, Slim Pickens rides Resi into orbit. Okay, so the spacecraft worked very, very well. And this is an example of one of the first events that we analyzed in detail. It was a flare that occurred on 23rd of July, 2002. And when we did this spectroscopic inversion of the hard X-ray data, with exquisite resolution, you can see these little look like error bars are really not error bars. They are the widths of the energy channels. The height of that, the thickness of the line is real. These are vertical error bars, if you can even see them. And what we saw, which we really didn't expect, was this little dip and a bump again. Instead of the spectrum kind of monotonically decreasing, we found it went down then up again. Now, I haven't got time to turn this into a class in plasma physics, but that's very, very difficult to do in a plasma. It's something called the two-stream instability. If you take one group of particles and move them through another group of particles where the differential velocity exceeds a certain critical number, all kinds of interesting nonlinear wave effects happen, which interact back on the particles to flatten them right back out again. It is almost impossible to sustain this, at least locally. And so all kinds of stuff went on. Well, is this real? Is it not? And there was about a year's worth of debate as to whether we could really believe this, bump, because the photon spectra didn't look that interesting. The photon spectra looked pretty bland. But when you did this regularized inversion, because of all the exquisite way that you get information on electrons at all energies from photons at a single energy, the believers said, yes, this is real. Plasma physics people go worry about this. The plasma physicist people said, convince me. So we did something called a blind inversion test. In blind inversion test, investigator 0, that's me, made up a bunch of electron spectra. There they are with all kinds of interesting, probably completely non-physical artifacts in them, including wedges and cutoffs and bits that went up and down. And these are the photon spectra corresponding to the 4 electron spectra on the left. They look not exactly identical, but you wouldn't casually observe these 4 spectra and go, oh, wow, look at that green one. That must have a big cutout of it or something. Because of the filtering effect, that at a given photon energy, you're studying all the electrons above that energy with different weights given by the cross-section. The photon spectra look pretty similar. So the question was, could we, in fact, take these photon spectra, apply regularized inversion algorithms, and recover these somewhat unusual-looking input spectra? To make this realistic, I didn't tell investigators 1 through 4 what the initial spectrum were. I kept it secret. I did calculate the photon spectra. I then proceeded to add noise, data noise, consistent with Poisson statistics on a typically flare-sized event with those spectra, and I sent them these photon spectra as if they had just been observed. And I said, okay, folks, calculate the electron spectra corresponding to them, which they did. So I did that. Investigators 1 through 4 tried 4 different methods. First 2 regularized inversion methods using slightly different techniques and slightly different ends of the energy bins. It turns out that's important, believe it or not. And number 3, done by someone right here at Rice University, where we basically took the matrix and made it square, stopped trying to worry about all the electrons of energy higher than the photon energy observed, and simply did a block matrix inversion where, recognizing that inverting a 50 by 50 matrix was going to be difficult, you just partition the matrix up into blocks of a sensible size so the matrix inversion isn't quite as ill-posed. And investigator number 4, who simply did the tried and true method of forward-fitting functional forms. So assumed a parametric form for the electron spectrum and deduced the best values of the parameters by some kind of least squares type analysis. Investigators 1 through 4 were free to add their own noise to the already noisy data to produce different realizations of that data. And by performing inversions on the different realizations, you get what we call a confidence strip, and that gives you some idea of the uncertainty in the results. They were also free and encouraged to calculate the so-called photon residuals. Once you've generated an electron spectrum corresponding to the data you were given, you can forward fit that through the Bremsstrahlung equation to get what the photon spectrum resulting from that would be and compare that to the spectrum you were given. And that gives a set of residuals. And if the residuals cluster, it tells you there's something wrong. The residuals should basically be randomly distributed simply due to data noise. If the residuals are clustered in some way or are too large, it says there's something wrong with the method. I almost apologize for the next slide. I debated half an hour ago at the back of the room whether I should show this or not, but it's very, very busy. But let me just try and summarize what's going on here. At the top 4 panels are the 4 cases of case number 1, 2, 3, 4. There's actually 4 more. We did about 8 of these things, but there's 4. And here are the investigators 1, 2, 3, and 4, whose names happen to be Anna, Edward, Chris, and Gordon. And these are the recovered spectra that they obtained compared to the dashed line, which was the secret one that I had generated without telling them what it was. And he said, did a pretty good job. Here's this, I thought case 2 was fascinating. This little notch in the spectrum, this little actually bit missing, was reproduced fairly well. Chris here had to use different energy bin sizes at different places to get the method to be stable enough. We felt sorry for the poor forward fitting person because, of course, the forward fit analytic form cannot produce shapes like that. It's just not within the capabilities of that parametric form. And what they found was that, yeah, they completely overlooked this, but they made up for it other places by subtracting electrons somewhere else to make up for the extra ones they added over the notch. These are the photon residuals, and they distributed fairly randomly, showing the method's working. The bottom here is what I call the cumulative residual. You just add the residuals up as you go forward and forward in energy. And if they're randomly distributed, that should kind of converge to an average number close to 0. It shouldn't show any significant bumps. And you can see the forward fit method, yeah, there's some clear deviations here, which is not a bad thing. The forward fit people said, yes, we did it, but we know the result is bad because the residuals are not good. When we calculate the photon spectrum from our parametric electron spectrum, it doesn't match. And it doesn't match here in one sense, and it doesn't match here in the other sense. And that gives us some clue that we might be missing something. Maybe we can adjust our parametric form in some meaningful way to accommodate that. The regularized folks didn't have to worry about this stuff. They just fit it away. And even Spectra, say, which had 4 orders of magnitude hills up and then down again, they did a pretty good job. They got the turning point. So we do believe the method can work, that any feature that it generates is probably real. It does match features that I invented in the first place, and therefore that these bumps and so forth in the spectra that are generated from real data have to be reckoned with. So, quick couple of summaries. Again, we can, in principle, extend the domain of the electron spectrum beyond the dashed black line here, which is the maximum photon energy that we're given. But it's a little unreliable, but it's possible. Sharp features can be identified. They're smoothed over, but they're still obviously there. Forward fit methods just can't do that. The parametric form can't accommodate these features, but it makes up for it in other ways. And more importantly, it knows it didn't do very well, and it gives you some clues where to look for solutions. And the square matrix inversion method can't go past this dashed black line, whereas the regularized inversion with this augmented triangular matrix can. Okay, now I want to talk about spatial inversions, a whole different thing. So let's recalibrate here. RESI was designed not only to produce exquisite spectral resolution, it also gave spatial information. Now, hard X-rays, which are photons like 20, 30 kilovolts, cannot, at least could not back then, be imaged using mirrors or lenses or traditional optical techniques. Instead, you have to use an occultation technique where you let the electrons in at place A and block them at place B and use the sort of pattern of intensities that results from that to provide limited information on imaging. So I'll try and illustrate this. Here's the spacecraft. It's got 9 detectors at this end, here. It's got 9 grids here and equal grids there. So they're matched pairs of just parallel grids. And they're made of either tungsten or gold or some X-ray absorbing material. And if you have a space between the grids, the X-ray gets through, but if they hit the metal in the grids, it gets blocked, it gets absorbed. And basically, if it has to make it through both grids, then it has to come from a certain direction, and therefore you learn something about the location of a source. Let me illustrate this. The simplest way to look at this is not to think of the spacecraft rotating, but to think of, if you're a bug on the spacecraft sitting still, it appears to you that the whole universe is spinning around the spacecraft in the opposite direction, much as when you go to the South Pole and North Pole and look at the stars in the sky, sure, looks like they're spinning around in circles. They're not. The Earth is spinning, but it's the same effect. So if you're sitting on the RESI spacecraft, you see sources in the sky doing circles at about once every 4 seconds. Then you go ahead and think of 3 hypothetical point sources, the green one, the red one, and the yellow one, and let's see what would happen to them if we put some occulting grids in front. There's the grids. We're going to put those in front of these things. Now, this is Lexi, and Lexi knows how this works, because this is a garden fence. And if you're a dog running the fence, and Dad is on the other side of the fence, you see him, you don't see him, you see him, you don't see him, and by timing the when you see things and when you don't see things, you can actually deduce a fair amount of information about not only where Dad is, but what shape he is. Here's the red one. As the world rotates around the spacecraft, it makes a circle, and if you can count them, it will flash on and off 16 times. It will flash on and off quite quickly here and quite slowly at the 3 and 9 o'clock portion. So you get a characteristic temporal pattern from a point source located where the red one is. 16 flashes. If you take a similar source located at a different angle on the sky, but still the same polar distance from the axis of rotation of the spacecraft, you'll get exactly the same pattern, but it will be phase shifted. The slow and the fast will occur at different times, and that's your clue as to where the source is azimuthally in the sky. The number of flashes basically tells you its radial coordinate. If it's closer to the angular rotation axis, you get fewer flashes. Just count them up. So in principle, it's easy. We simply observe a point source going round, and we count the flashes, and we decide when they're fast, when we're slow, and that will give us the polar coordinates of that point source. And if you have enough polar coordinates of enough point sources, you've made an image. The trick is to do like this. There are the modulation patterns produced by different sources of different, polar coordinates and of different sizes, because eventually if the source is big enough, you see always half of it at any given time. It's not modulated, and the intensity of the pattern goes down. So your challenge, if you like, quantum mechanical basis type equations, is here's a modulated spectrum. How many of each of these characteristic patterns above do you need to sum together to produce temporal modulation pattern number 7? And that's the essence of extracting imaging information from these so-called rotating modulation collimator instruments. I like to tell people it's patterns, not pixels. You don't make an image the traditional kind of TV manner by scanning and putting dots on the screen. Rather, you see the whole sky at once, and you see a pattern as the spacecraft rotates in this 4 seconds. You see a temporal pattern, and that temporal pattern corresponds to a certain type of source, and you're overlaying those patterns to produce a whole image. So here, for example, is a fairly kind of raw image from RESI, and you see all this red stuff here is not real. These are kind of side lobe ringing artifacts of the real source over here because you've truncated the Fourier series. You're essentially making spatial Fourier components. You have a limited domain of when you can study the spatial Fourier components. So you've got a truncated Fourier series, and when you invert it, not all the terms that should cancel, cancel. We call these, and radio astronomers call them these first visibilities. They're basically spatial Fourier components. U and V correspond to essentially Kx and Ky. And so the visibility pattern of a source is its real intensity pattern with a spatial Fourier transform in 2 dimensions applied. Here are the Fourier components observed by RESI. You can observe a Fourier component on any one of those circles because each detector has a different pitch and therefore measures a different Fourier component. The dots are somewhat artificial. You can observe any kind of range of angles you want, but get to enough statistics, you have to let the spacecraft rotate for a certain angle. And so you get typically about 20 or 30 points on each circle. For radio astronomers, this is a very sparse set of data. They are used to having millions of visibility components. We have about 100. And so we had to develop some clever algorithms to take sparse Fourier data and turn them into images. Here's just one. It's called UV smooth. The picture here, which I hope you can see, basically just a bunch of delta function spikes, which are the Fourier components we actually measured. And if you invert that, you get this kind of spatial profile here, which looks nothing like the dashed line. There's all this extra stuff because you've only got a finite number of Fourier components. This is an attempt to smooth this out and essentially invent Fourier components to fill in the gaps in a smooth way, coupled with a positivity constraint, because we do know that the real image is necessarily positive. And after you get clever enough with this, you actually do a pretty good job, and all the side lobes go away. So what we really want to know is what is the electron spectrum at the acceleration region, and how does it change throughout the flare as the electrons propagate. So we'd like to look at the electron spectrum at different positions in the flare. In principle, we thought this would be easy. Okay, we take the visibilities and we make a photon-based picture out of them. So here's the photon image between 10 to 14 kilovolts and so on. Then we look at this little interesting region on a square, and I know the photon flux between 10 and 14. I know the photon flux between 18 and 22. I can get a photon spectrum at that point, and it looks like this. But if you remember the blind inversion problem, photon spectra that look remarkably similar can yield electron spectra that are remarkably different. There's a tremendous amount of amplification of noise and uncertainty to the extent where you actually try and calculate the electron spectrum in that square, you get all these bumps and wiggles, most of which are not, in this case, real. They are due to uncorrelated photon noise between those different images. And this was a serious problem for a long time. Until I worked with some folks in Genoa that do medical imaging, primarily working in inversion problems, but they looking at the sun to some extent is a similar remote sensing problem to looking at a tumor inside somebody's body. Some of the mathematics comes over very well. They said, look, you're measuring the data essentially at limited Fourier component points. Why not invert the spectra only at those points? Recognize that the process of spectral inversion and the process of Fourier spatial inversion are both linear, so it doesn't matter which order you apply them. And it makes actually more sense to apply them the other way. Here's a traditional way. You take these temporal profiles that my dog sees when it's running the fence, and you get photon Fourier components out of that. From that, you make a photon image. You take all the photon images at different energies and you make a stack, and you essentially look down through that stack of images at the point in question to generate a photon spectrum at that point, and then you invert that to get an electron spectrum at that point. Then you put them all back together again to get electron images. Does it not make more sense, given the type of data we have, to do it the other way around? First, take the photon visibilities, which are information on the spatial Fourier components at a specified point in UV or KX, KY space, and do the spectral inversion on those first to get what we would call electron visibilities, which are Fourier components of the electron map. Then we've got all kinds of standard image processing techniques to go from electron visibilities to electron images. So you simply reverse the order of the steps, and it turns out that works extremely well for this type of data. Again, it's kind of engineered for the type of data we have. To show you that working, here we go. Oh, sorry, quick couple of points. Because you go from the photon UV spectra to the electron UV spectra using a regularized inversion, spectral inversion process, the electron visibilities vary smoothly with electron energy, as opposed to the photon visibilities, which don't, because the data are in different bins. They have uncorrelated data noise. The electron visibilities necessarily vary smoothly with energy because of the regularized way in which they are produced. Therefore, when you take them and make images out of them, the images vary smoothly with energy, which is probably a physically reasonable thing for them to do. Here's what it looks like. We've already seen the top figure. This is what you do the kind of old-fashioned way. You make the photon images, stack them up, look at the photon spectrum at each point, then do the spectral inversion. Here's the clever way. You first do the spectral inversion to get electron visibilities, and then you make images from them. Notice the energy can go higher than the maximum photon energy observed, because in the regularized spectral inversion process, that upper diagonal matrix, you can go further than the maximum photon energy you see. So we actually get images of the electrons at higher energies than we get images of the photons directly, and they vary smoothly with energy because of the way they're constructed, allowing us to make beautifully smooth electron spectra at different points within the image, which allows solar physicists like me to learn things about how the electrons are accelerated and so forth. So, you can read. Yeah. You know, we have been able to use this very novel design instrument, which has its strengths and limitations. The major limitation being it observes not images, but Fourier components of images at only a sparse number of points. But because necessity is the mother of invention, we've developed some really kind of sophisticated algorithms to make the most use of data in that form, allowing us to address the science goal, which is how does the electron spectrum vary from point to point within the flare. One of the things you can't change is that this instrument measures the whole sky at once. You can't focus in on a particular region. You can't block out any part of the image. You just can't do that. And therefore, there is a dynamic range problem. If you've got a very bright source over here and a very faint source over here, you'll never see that faint source because the Fourier components of the bright one will swamp whatever Fourier information you're getting on the less bright one. To look at that bright source, you have to use direct imaging optics, which is where we're at now. I mentioned we couldn't do this 20 years ago. We can now. And NASA is currently exploring various possibilities for doing direct imaging in these energy bands, which is a whole different type of inverse problem involving not so much Fourier components as deconvolution of point spread functions of the instrument itself. I'd like to thank the Mafia, as they're known, which are the folks in Genoa, Edward and John in Glasgow, the whole RESI team for building an absolutely superb instrument which worked perfectly for about 16 years. And last but not least, this is the International Space Sciences Institute, which funds little mini conferences, lets 7 or 8 people who would otherwise probably never see each other to get together and share ideas and produce results like this.